Today, as Professor already mentioned, we'll be talking about looking at biochar in terms of how it can help as part of circular economy approaches. These days, we always talk about circular economy, sustainability. These are the new kind of, you can say, buzzwords or whatever you want to call it. We all, if everything we talk about how to bring circularity. Biochar, it's not a new topic. People have been working on biochar for many, many years and maybe decades. But it has been renewed interest in recent times, especially from energy application and environmental systems application as well. So remediation, different types of biochar as a soil amendment has been used in past for in many research papers. You will find that. So today's presentation is essentially as when I was talking to Professor Reddy, it's mostly the PhD work of these two gentlemen who are also in the audience. Dr. Sahil Chauhan, he recently defended his PhD, and Unni Krishnan Menon, who is waiting to defend his PhD. So he has also submitted his thesis. So he's waiting to defend his, and both of them are there in the audience. So I requested them to join because it's essentially nearly 50 to 50% of the slides are actually from their PhD work. And if you have some tough questions, so they are also here. So that's the reason I thought that it would be good to have them too. So let's get started. So whenever we talk about let me get this pointer here as well. Yeah. So see, when we talk about this these days, the sustainable development goal, try to reduce the fossil fuel, go towards renewable energy. So world population is increasing. We are using more and more fossil fuel. We are seeing the impact of climate change. There is always a demand for clean energy sources. Environmental issues are also getting a lot of attention these days. We have a sustainable development viewpoint. SDG goals are there. From time to time, these things do take a back seat because of certain political, economic, and other situations. But overall, we are very much concerned about environment. I will still say we are very much concerned. Sometimes the policy and other things, unfortunately, things always goes like a curve. So things go up and down. So we don't worry too much about that. And I'm being a very optimistic person. So we have to take care of this environment. So there are always interest in terms of going for eco-friendly material. So one of the stuff that we use a lot is a graphitic carbon. And so one of the things is that can we use this waste sources to produce graphitic carbon? There where this biochar, hydrochar, pyrolysis and all those technologies comes in picture. And many of these organic waste, if you don't do proper management of this organic waste, they will end up in the environmental system, and then during the aerobic process, they will produce CO2. In anaerobic process, they will produce CO2 and methane. So both are greenhouse gases, and they will create problem in terms of global warming, climate change, and all that. So one hand, we can do some useful diversion of that, produce some value added product, and try to bring circularity so that we don't have waste going into the landfill. We are actually doing some good out of that waste. And that kind of helps in our SDGs as well. In fact, in many of the SDGs, predominantly you can talk about in terms of clean water sanitation, climate action. If you are taking care of these different types of waste, they don't end up in our ocean, in our river. So life below water. This is just some example of SDGs. In fact, they do impact directly or indirectly almost all the 17 SDGs we can think about, which we have. So global energy demand, if you look at over the last 5 years, from 2020 to 2024, or you can even add now 2025, what we see predominantly the red one is the coal. So you see that coal is around around 30%. That's what you see 20, 21, 22, 23, 24 last 5 years. So coal is around 20%, 20, so 30%. And then you have oil. Oil is also quite a bit. The natural gas, nuclear and hydropower. Then we have renewables. If you take the renewables, mostly it's a biomass and waste, which is 45%. Hydropower is 25%, wind, solar, and others is around 2%. So hydrochar and biochar, they could be a carbon material which can bring multiple benefits, and at the same time, they could be a good source of our like an energy source as well. And it could be a good soil, like a carbon capture. It can lock carbon with a system for hundred to thousands of years. It can mitigate greenhouse gas emissions. So if you do a sustainable biochar implementation, we can actually offset nearly 12% of anthropogenic greenhouse gas emissions. So where are the different carbon material? What are the potential feedstocks from where we can produce this biochar or hydrochar? So I'm not going to list them. You can see, of course, see on this slide, and this video will be available to you. But there are variety of feedstock is there, and many of these we have tried in our lab. We have worked with yard waste, we have worked with food waste, we have worked with cigarette filters, and we have also done some work with sewage sludge, and other people have done a lot of work with that as well. So this fits, we can produce this carbon material, and they can have variety of application in terms of soil amendment, which has been done for a long, long time. Also removal, because this carbon material could be potentially replacement for activated carbon. So they can also be used as an adsorbent for water and wastewater treatment. Isn't that says there? They are what we have seen that they can also be used in energy storage, which I will show you later on. And it would be used as energy storage, can help in anaerobic digestion. A lot of research is going on in that area where we are also trying to do some work. And then also in terms of dark fermentation for production of hydrogen. So for each one of them, each one of these applications, we had a chance to work based on, as I told you earlier, Sahil, Unni, and then I had other, Raja was there earlier, and then some more students, master students who have worked on this particular area. So we had a chance, because of the different projects we had a chance to work on on all these different applications, little bit or slightly more. So in terms of the feedstock, that typically municipal yard waste, agroforestry waste, food waste, and all sometimes you can also use plastic waste, but there is always a concern using of the plastic waste. So and then there are different ways of you can make biochar or hydrochar. People talk about biochar, and there is also some hydrochar. You can do hydrothermal carbonization, or you can go for torrefaction, which is kind of a char also, like at a very low temperature, around maximum 300 degrees centigrade. You can produce torrefied char or torrefied charcoal. People say that pyrolysis reactor, you can do biochar from there as well. You have different kind of feedstock. And we can also try to do first anaerobic digestion of, say, agroforestry waste, food waste, produce that biogas, use that biogas, and the sludge coming from there could also be either done hydrochar or by hydrochar, or it could be it could be used as a co-feedstock, not only a single feedstock, but could be used as a co-feedstock. Recently, we published a paper on food waste and sewage sludge together in terms of how they do it. So I'll start showing you some of the examples of what people have worked on. So valorization of organic fraction of municipal agricultural solid waste by HTC, quite a lot of papers you will see, and our group also contributed quite a bit. So there we have looked at the food waste from the university campuses like our campus, use this hydrothermal carbonization reactor, produce this hydrochar, and that hydrochar could be used as a partial substitute for coal. So that it basically, if you look at the H by C and O by C ratio, it kind of comes out to be a more or less lignite type of coal which you can use. So it's and then there are it can produce newer types of jobs. It can mitigate the greenhouse gas emissions, and you can use it in a possible gasifier and those kind of application. Then we have also done some work where it is not like where you have CO2 captured from a your like a Jindal Steel and Power. Jindal Steel and Power from there. Those of you who are from India, they have a plant in Angul, which is in the state of Odisha. Those of you who are from outside, we're in one of our eastern states, which is called Odisha. There is a Jindal Steel and Power plant. So the CO2 emitted from the Jindal Steel and Power plant, we have collected that CO2. It went through a photobioreactor. They produced this microalgae. That microalgae was brought to our lab. We did that hydrothermal reactor. We produced this biocarbon, and this biocarbon was further modified to produce this like a biocarbon electrode, which can have potential application in energy generation and storage in terms of supercapacitor, batteries, and fuel cells. So those applications, so these are Yeah, so it's on the lab scale, most of these technologies have been demonstrated as well. Several patents are also there. When in the some are also being done in the pilot scale, but when we go actual in a kind of field scale, it's still there are things are kind of needs to be worked out, especially the feedstock quality. The feedstock quality and getting the consistency of the feedstock, that becomes a big question mark. So that's it becomes an issue. One initial work, what was that prospects of using single-use plastic and biochar composite as a solid fuel and a soil amendment. So the single-use plastic, we know that it doesn't have much of use. So, like, it doesn't get recycled. It always gets littered, and then finally we find it always getting into the drain, and then finally to the stream, and to the ocean, and we have all those great Pacific garbage patch and all that. So we have looked at single use plastic, and then biochar, which was actually eucalyptus wood, and they produce this biochar in like a traditional pyrolysis system. And the char pellet was used as a fuel in the Ford's draft cooking stove. Char pellets was also made. And then we looked at, we also used char in commercial organic agriculture, application of char and phytoremediation of the mining dump sites. So those are issues were there. There was always a concern little bit, since we're using the plastics. There is always some concern of certain contaminants getting into the environment. So based on some of the preliminary testing that was done, we did not find of much of a concern. But there is always whenever if you're using plastics, you always have to be careful. So that's definitely this was Raja's part of the Raja's PhD work, and as a PhD defense also, he had a lot of questions was there in terms of use of plastic in this application. Yard waste pyrochar as a carbon electrode for supercapacitor. This was help is like a demonstrated in the lab, where we had took the yard waste, we did the hydrothermal carbonization pre-treatment around 200 to 250 degrees centigrade. Microstructural tuning was done, then slow pyrolysis of that material to up to 800 degrees centigrade. And then we three electrode testing and symmetric supercapacitor fabrication was also done of the selected material. So this was done in collaboration with our multifunctional energy material laboratory in physics department, Professor Amrish Chandra, who is a colleague of mine and a very close friend. We try to do a lot of work together. So it was done with his support and in his lab, where we produced this electrode material, and we saw that it could be used as a energy storage material as well over there. So as some of you might be familiar with our work these days, anything you do, any new material, anything you come up with, there is always a thing that you have to do life cycle assessment. You have to show the LCA, carbon footprint. So we looked at that supercapacitor in terms of, and most of the LCA that you find has a very good energy density. Supercapacitor delivered around 773 watt hour per kg energy density and 34 watt per kg power density. The major problem in terms of carbon footprint, environmental footprint, was electricity consumption. When you make this stuff, if you keep on using fossil fuel based energy, that always becomes an issue. That was the most dominated environmental footprint. Then we had this bio-based carbon electrode, where we use cigarette filter and yard waste. This was the work of Unni Krishnan Menon. He's who I introduced at the beginning. He's almost done with his PhD. Very soon he will be finishing, like he will be defending his thesis. So it's where he was looking at yard waste and cigarette filter. Because both of them does end up into the environment and creates all sorts of problem. So can we utilize this waste through co-hydrothermal carbonization and pyrolysis, produce this porous carbon material, and that porous carbon material can be used as a supercapacitor application. So where we found that if you look at this electrode that you make, and then you end up making these coin cells as well, like batteries. So we looked at the environmental impact due to the production of these coin cells, and both as production of coin cells, cell fabrication stage, electrode preparation stage, and different environmental profile was found. So as you can see that for each one of these, like a key environmental hotspot was electricity consumption. That emerges the dominant contributor to overall environmental impact. Electrode fabrication steps and associate machineries were identified by major impact sources as well when you look at the process-driven impact. So how will you mitigate? Renewable energy sources is strongly recommended for that. And for this, we used a gate-to-gate LCA framework, mostly focused on electrode manufacturing stage, and functional unit was taken as 30,000 coin cells per day. Uh, then kind of taking it further, Unni is also a joint PhD student with University of Alberta, where one of my close friend, Dr. Amit Kumar, he is in that energy and environmental systems. So they also have continuous pyrolysis setup. So their part of the work was done over there, where he only was looking at in terms of softwood derived biochar, where you can see that Hooper, then you have the intermediate pyrolysis, preheating zone, pyrolysis zone, and then you have the solid dropout pipe, and the syngas is being analyzed, oil was being captured, and taking those, we are trying to look at whether this particular softwood derived char could be used either for supercapacitor or for solid fuel. So although we did find that electrochemical performance was quite modest for this softwood derived biochar, but it exhibited favorable characteristics as a solid fuel. So rather than uh, as a electrochemical performance, we found that possibly it is more suited for a solid fuel. So kind of just tells us that not all biochar are inherently suited for one particular functional application. It keep on changing, like based on the feedstock and based on the process as well. You may have different kind of, you can come up with different kind of applications. So here you can see that different, this is softwood in terms of its different temperature, as different temperature ranges and the retention time. So you can see that H by, this is Venn Canulin diagram, so O by C and H by C ratio. So most of it was kind of in this particular region. So H by C, O by C value fell within the range typically of bituminous coal, which you can see from the diagram. And this dotted line has been blown up over here. So you can see the differences between different types of treatment protocol. So here, as you can see that as per ISO guideline, standard pellets density for export is around 600 kg per meter cube, and for most of them, as you can see over here, it was kind of more than 600 kg per meter cube. And then HSV was kind of ranges from around 19 to 28 megajoule per kilogram. Then we have, if you look at the fuel ratio, which is a fixed carbon divided by your volatile matter, uh, industrial coal has which is used in power plant is 0.5 to 3, that is the range. Now this softwood biochar, it is also within this range only, 1.8 to 2.9. So volatile matter is more, that means burning will be quick in the power plant, but it can potentially replace coal if you go for this kind of for that particular application. So that was more on the energy side. Then the environmental side. So here, this is the kind of work coming from mostly Sahil's work. Sahil, as part of as part of his PhD thesis, he was trying to look at, can we use this char, this engineered biochar, for water and wastewater remediation for some of these emerging contaminants. So how we can do that? So utilization of these physicochemical properties of biochar and turning it into for some adsorptive or photocatalytic based application. So as you can see, biochar has certain physical properties and chemical properties. Physical properties in terms of density, specific surface area, pore size and volume, particle size, and all these are important for certain application. Similarly, for chemical properties, your elements and pH, conductivity, CECs, cation exchange capacity, what functional groups it has. So we can work with certain in terms of different feedstock, we can try to modify this biochar for the semiconductors, or we can activate activation with kind of certain chemicals, for example, KOH, HNO3. Then you can also put some functionalized material, so metal or other atoms. You can activation by gas could also be done. So it can be used for photocatalytic hydrogen production, for air pollution and other application can be done for treatment. CO2 phyto reduction, those can be used. Abatement of water pollution if you if you modify this biochar. So those things were explored as part of this PhD work. So in terms of biochar modification or engineered biochar as we call it, there are different types of ways you can go about, and there are different mechanisms are also there. So from the literature, again, this is Sahil's work. He was looking at the different feedstock, and with the thermal process you produce this biochar, and then you can do certain modification. Again, I'm not going to read each one of them. As I said, this video will be available to you, so you can always kind of stop the video and look at a slide in more detail. So this is you have your like a zinc chloride physical modification. You can do chemical modification, and then you can have metal nanoparticles loading, like those things, preloading with silver nitrate, copper nitrate. So you can have some surface functionality. You can do those kind of modification. So general strategies for biomass. This is the general strategies and impact on different properties. So if you put alkaline, enhances the surface area, introduces the oxygen containing functional group. If you put gas and steam, improves the biochar structure and enhances surface area. Metal oxide, then you have a catalytic performance can get enhanced. You have more magnetism and adsorption. Then you can have carbon material which enhances the surface area. Better the surface area, better the adsorption capacity. Acid can eliminate impurities, introduces the acidic functional group. So based on these kind of different types of treatment, we can make biochar do certain things based on what we really want it to do in terms of the remediation of water and wastewater or those stuff. So as you can see, these are again these different types of reaction which can potentially take place, and these are coming from these papers which has been referenced over here. So there was always a challenge. So when we started with this work, there was a challenge that can we come up with this biochar quality index development? Can we come up with an index which we can use for so if you have a certain feedstock, for example, you have this mustard straw, sugarcane bagasse, rice husk, coconut husk, wood savings. So you have all these different feedstock. So we will produce this biochar. We can do further some sort of pyrolysis, and then we can come up with this nice like a char material, which could be used for say your adsorpted removal. So here in this particular one, we use this antibiotic removal, which is sulfamethoxazole, which is in short form we are calling it SMX. So it was from water using best strength biochar obtained for BCQI approach. So we use this BCQI approach, do the CHNS analysis and all those. These are the different parameters we looked at. All these different parameters. So based on those parameters, we come up with these numbers, the normalized value for parameter in terms of which is the minimum value of the parameter, maximum value of the parameter, and then we come up with this normalized value. And then BCQI was kind of a summation of your going for this is W shows the weight respective to each parameter in concentration, and U is the indicates the normalized value of the parameter. So based on that, and J represents the each parameter, and N is the number of parameters. So based on that, we come up with this BCQI value, and we try to rank them at 1 to 6, where biochar ranking based on BCQI score. And when you see that 6 was kind of on the higher side, and based on those target application, here was the adsorpted removal. So for that we ranked it accordingly. So if your target application is something else, you will kind of take a different, will take a different approach. So the different parameter was selected, correlation, factor analysis, as you know, these kind of like a things that we do. So for different types of biochar that we made as part of this study, as you can see over here, that BCQI ranking. So the number one, which represented as SCB 750. So that was biochar. It is basically treated up to 750 degrees centigrade. So a representative correlation matrix in the figure A, we are showing the correlation matrix with the P less than equal to 0.05 for the 19 initial parameter. Then weight distribution was shown in selected parameters for BCQI. Then with the ladder type schematics showing you the in terms of rank biochar. Then Sankey schematic, which is showing the individual BCQI score for the final parameter. So based on that, we looked at so the best quality, which came out to be the best rank biochar. We use that for the further our kind of research. So this is a summary of individual and aggregated value. Again, as I told you, you will get this. No point reading each of those numbers. So here, based on the percentage removal of SMX and we try to correlate with the BCQI score. So as you can see, the one which had higher BCQI score tended to have better removal. So there is a comparative representation of adsorptive removal of this contaminant along with what was the quality score. So it kind of just matches with that as well. So, and then these are the BCQI score for different types of biochar. The work is already published, and it is also, it does come, it was put on the cover, front cover of this journal as well. Then we looked at can we go for that was mostly on like adsorptive removal. Then if you do the biochar supported 2D WS do as a photocatalyst. So we had this SCB integrated WS2, this SCBW, the nanocomposite was formed, and that was then we did some process optimization using this Taguchi. We call it a Taguchi design, and the preliminary OTC degradation profile shows 90% percent was with SCBW10. So these are all those different kind of your uh, those radicals which is there. So you can see its performance in the figure. You can see in terms of photocatalytic degradation of OTC under visible light. OTC is your oxytetracycline. So in this case, how it was degrading as a function of time. And this diagram kind of tries to explain the mechanism of the degradation pathway. And then we also looked at the toxicity aspect of that as well. So this was again performance of quality as a photocatalyst. Again, the effect of humic acid, effect of OTC on degradation efficiency on the real water and real wastewater matrices, role of excavating agent, the stability of on 4 consecutive reusable cycle under visible light. So we were kind of doing the variety of temperature conditions, and based on that, we looked at this performance. And then we also looked at, in terms of the degraded products, whether there was any, did this seed germination test, like Sahil, as part of his work, did that. So these are the digital photographs. So 40 milligram is stock solution, as you can see this one. Then you have the DI water, then you have those those contaminant concentration at different level, 5 milligrams per liter, and then you have your after so like a 60 minutes, 120 minutes, 180 minutes, 7 days, and average and maximum root length. So what it was found that it was found to be not that much of a kind of in terms of the toxicity. If you can look at a kind of toxicity part, it came out to be that experiment did found that it was not that much toxic there as well. So based on this, this is kind of the work that we have done on energy and environment application. But on another, this is already done. And some of the work, which is the ongoing work right now, is we're trying to look at how this char could be used in enhancing in anaerobic digestion. These days, like we are today, during the day, I was in Kolkata, which is, so those of you from India, you know that we were meeting some of the state officials, and I think some of my kind of friends and colleagues from the state government is also in audience right now. When they were joining, I could see their name. So we were talking about whether it's possible to do a kind of a CBG plant in one of the city in West Bengal. So in CBG is getting quite popular. It's a compressed biogas anaerobic digestion plant. Government has several scheme in terms of the Satat scheme and all that. So whenever we go for anaerobic digestion, for the economic viability of a anaerobic digestion plant, we need to make sure that we kind of capture good amount of gas. So what we have seen in work being done globally as well, where people have used this char as a kind of which is helps in terms of enhancing the biodegradation process in a anaerobic digester. So we'll talk about that in next few slides, like how is happening that, and what we are trying to do some work in that area, along with some work in terms of how it could be used for hydrogen production as well. So this AD is involves the breakdown of biodegradable material in the, as you know, absence of oxygen. So you can use variety of feedstock to produce AG, manure, wastewater, biosolids, food waste, other organics. Only thing what you need to really make sure that you don't have much contaminants coming there, no metals, no plastics. Like a zero plastic will be the best thing to do. And from there you can produce biogas, which could be electricity, heat. It could be used for vehicle fuel, renewable natural gas, or you can also use as a digested, the sludge coming out for a horticultural product, crop irrigation, annual bedding, and all those different applications. So when we talk about this circular economy mod for traditional and innovative AD, so traditional AD, we have the organic waste, we take it to a reactor, we produce biogas, the digested we use as a soil fertilizer. So it includes biogas production, biogas upgrading for like a social production or domestic use, digested applied as biofertilizer, crop growth and all that. Innovative AD says that you try to take this, you have this organic biogas, from the organic waste, you have from this digested, you part of the digested you use at soil amendment, part of that you can also use, you can produce biochar, and that biochar could be used in terms of as a soil amendment, and the biochar could also be used within the anaerobic digester for enhancing the bioanaerobic activity, anaerobic like degradation activity. So biochar prepared from solid digestate can be further used as an AD promoter. So that is how, in terms of how biochar helps in different stages of AD. So when we all know these are the basic steps of AD: hydrolysis, acidogenesis, methanogenesis, where you have hydrolysis, enriched hydrolysis bacteria increases hydrolysis efficiency. So when you integrate biochar, it kind of helps in terms of all these aspects. Is stimulated BFA production rate when you have biochar. Yeah, increased BFA yield also. Accelerates BFA's generation during initial period. Methanogenesis achieves higher methane yield, improved methane production rate. So these are already demonstrated in lab scale and pilot scale. So for each one of those stages, if you have this biochar there, it does help out. So as you can see over here on the y-axis on the right-hand side is your biochar dosage, gram per liter, and this is your substrate type. And on the left-hand side is a specific methane production, milligram per gram of VS. So if you based on biochar dosage, on the specific methane production, we see that for different substrate type, we do see that when we put biochar, it does help in terms of increasing the anaerobic, in terms of production of more biogas. So in terms of biochar and hydrochar and AD promotes immobilization of microbial biomass on medium and high surface area. It acts as a carrier for both hydrolytic microorganism and substrate. So increases the hydrolysis rate, enhances in terms of enhanced attachment and electron transfer properties are there. So it enhances in acidogenic and acidogenic as well as acetogenic bacteria. Alkaline nature of biochar can help buffer the pH, and that will help methanogens, stabilize environment for acidogenic bacteria which thrive in slightly acidic to neutral pH conditions. Then it decreases in lag phase, enhance microbial colonization, so that allows bacteria to grow efficiently. So biochar can absorb inhibitory substances, create more favorable environment for microbial growth. And it also helps in terms of amelioration of archaea community, promotes microbial colonization, it stabilizes pH, mitigates inhibitory compounds, and it also helps in terms of your direct interfaces electron transfer, which is diet between bacteria and methanogens. So biochar acts as an electron shuttle, improving the direct interfaces between electron transfer. Enhances, so here you have the diet process, facilitation of the diet process which is taking place. So it does help out. And similarly, what we have seen in the dark fermentation too, dark fermentation which uses anaerobic bacteria to produce biohydrogen. Right now, we are trying to do that with food waste in our lab as part of a Indo-Denmark project. So dark fermentation uses anaerobic microorganisms in darkness between 25 and 80 degrees centigrade or high temperature for biohydrogen production. So along with hydrogen, you get other gases there too. So its primary source, of course, is the glucose molecule that occurs in carbohydrates and other feedstock. So you have this biogas sampling and stuff. So when you add schematic, if you this is how this, like you have a glucose, you produce two pair with the acetyl CoA. So what you do is you don't let it produce methane, and you just try to go towards more and more hydrogen. So you suppress methanogens and produces more hydrogen there. So biochar, it acts as a potential additive amends to the process for intensification of hydrochar production. It's basically porosity, element and compound composition, surface chemical functional group, pH, they all influence the hydrogen production in DF system. So formation of a stable biofilm of hydrogen producing bacteria, HPB, that regulates pH and facilitates better electron transfer, and its main factor responsible for enhancement of hydrogenesis. So this is the kind of your different pathway where you can use hydrochar your biochar for having more hydrogen. So this is again, it's effects on hydrogen yield, effects on pH stability, effect on volatile fatty acids and all that. So we'll go a little faster because I want to have some time for question and answer. And I think I've already taken nearly 35, more than 35 minutes. So it's in terms of, as you can see, there are, we can talk, if you have questions on that, we can talk about that later as well. So we also have worked on, in terms of taking this food waste, when we do this hydrothermal carbonization from this organic feedstock, and then you produce this hydrochar, then what is left is your liquid portion. So in terms of the circular economy, what you have to do something with the liquid portion as well, isn't it? So the liquid we have used as a liquid hydroxylate, the carbon source for this particular this organism, Cupria vedis nectar, and we produced like a PHA, which could be used for producing like bioplastics. And then we looked at whether these bioplastics are really biodegradable. So in terms of biodegradability in a composting system and anaerobic system. So very quickly, I'll show some of the papers, which is like we have worked on looking at, see, one of these hydrochar work requires water to be added. Nobody will allow us to add water, like pure water. So we looked at, can we use landfill leachate for the liquid source during hydrothermal carbonization of MSW. So that's, we did find that it's a HHV or hydrochar was comparable to traditional solid fuel, even with the landfill leachate. And so if you use landfill leachate, it can, sustainability process does improve. Then hydrothermal carbonization of renewable waste biomass. So this work mentioned Sahil and Unni Krishnan in our group. When I came back to India, this work, this hydrochar work was actually started by Haribhakt Sarma. So these are some of his paper where he's right now working in Singham Manipal University as assistant professor. So there we looked at different types of feedstock, especially food waste and yard waste. So we looked at can we do renewable energy generation as part of this biomass? Hydrochar densification was also done. Co-HTC was looked into. Larger scale, we looked at it. There is a potential to use this in a larger scale application. We also did some work on co-hydrothermal carbonization of food waste and yard waste. Then co-pyrolysis of plastic waste, which we already discussed. Molasses was used as a binder. Then hydrothermal carbonization of yard waste, looking at the combustion kinetics, energy properties, grindability, binderless fuel. If you have too much of lignin, you don't need binder. So if you have too much of lignin in your yard waste, then you don't need lignin. Actually acts as a binder. So those, so because when you add binder, that means you are adding something like molasses and all that. So rather, if you don't have to add binder, that is always better. So there are work also on mixed food waste, on looking at reaction severities, pelletization, then carbon prepared in landfill leachate in terms of energy storage capacity. Then some of the work which you already, we have done some work where looking at in terms of processed water from STC as a reaction medium. So rather than using fresh processed water, can we use wastewater with a significant reduction of the carbon footprint? And you are also doing a trade-off because you are not letting that wastewater being treated. So that's also good. So there we worked on that aspect. Engineered hard carbon. This is whether it can be used as a supercapacitor, what we need to do. Then some of the work from looking at harnessing yard waste as a carbon electrode. So we already published this work. We already discussed about these work in previous slides. So those are biochar quality index, which we discussed earlier too. Then photocatalytic degradation one. So this is our group. And then most of the hard work, they keep on working very hard. You can see Unni right there at the back, and Sahil must be somewhere right there. And then Hari is over there, and Raja is over here. So these are the people who have really worked on this area, but and Anjali is here who is working on that bioplastics. So because of all the hard work of these nice gentlemen and ladies and gentlemen, that I'm able to present these things at a regular interval in Professor Reddy's webinar. So on different aspects. And we have got funding from several sponsors, industrial sponsors, central government agencies, state government, foreign country collaboration. And this funding is not only for our this biochar, hydrochar work in general, for all the different work we do in the area of waste management, sustainability and circularity. So a good number of publications over last 10 some years. This is coming from there, and number of students graduated and all that. So thank you. So it was just I was trying to give a snapshot of almost like you can say three, four PhDs and masters work. So it was, but we'll be happy to answer questions, whatever questions you have. So thank you. I'm stop sharing my slide right